We're going to start talking about linear regression again. So we're going to look a little bit back at that linear regression unit and review some of those concepts. So it's a good kind of introduction to review to what we've been doing. Because this is our final new chapter. This is it. We've got 2 days of new material left, today and tomorrow. That's it. And we're done with new material. Okay? So this is the end. We've reached all the material you need to know for the AP exam after this. How about that? You should be excited. And that's good because that gives us 3 weeks of review time, which is awesome. But just kind of reviewing what we did with linear regression and looking at that idea again. This was a scattergram we had back from chapter whatever that was about percent of body fat versus waist size in men. It's a scatter plot of our data set. And as you recall, what we try to do with a linear regression is we find the line of best fit. Okay? We try to find that line that best fits that data, which means basically it minimizes the sum of the residuals. So every data point, the line here just represents a prediction. Okay, so y hat, we got our equation, y hat equals, hold on, let me make sure I get my b naughts and b1s right, because otherwise I forget them. I know there's a formula down here somewhere. So I don't know. Yeah, it's b naught plus b1x. Yeah, b1 is the slope, okay. So going back, we had y hat equals b naught, which is my y-intercept, plus b1x, where b1 is my slope of the line. That was the equation of that line. And again, what we're doing is we're finding the minimum residuals, minimum sum of residuals. And remember, every data point here has some sort of residual. Where, again, the line is representing my expected values. So the line represents expected values. And the particular dot represents an observed value. And guess what? Residual is observed minus expected. So when we're doing that whole chi-squared things with observed minus expected squared divided by expected, the residual here is just observed minus expected. A lot of people got that mixed up on the test yesterday because the residual for chi-squared is not just observed minus expected. So that happens. But for a regression, residual is just observed minus expected. And again, so we minimize the sum of all the residuals, basically. Well, the sum of the squares of the residuals, because we did the sum of all the residuals, it should be about 0. So that's what was going on with linear regression, just a quick review. Again, we're modeling the relationship between two quantitative variables. We have a predictor and a response variable, and we imagine a idealized regression line, which assumes means and distributions fall along the line even though the distribution values are scattered around it. Now, what basically we want to do is go beyond just the regression line and say, well, how confident are we about that regression line? So we talked about, the R squared and the R and some, the coefficient of correlation and the correlation coefficient and coefficient of determination. Okay, we talked about those values. So those are some blasts from the past that we'll probably have to go back and revisit again in our review process. We tried to estimate, okay, is this a good regression line? Isn't this a good regression line? We looked at the residual plot. We'd see if there was any pattern to the residual plot. All those sorts of things that we did to help determine, is this a good regression line or is it not? But what we haven't been able to do basically is give any objective standard to that. And so what we do now is we start giving some objective standard, not necessarily to the line itself, but what we can do is we can start giving an objective standard to the slope of the line as well as the y-intercept. Much more the slope. The slope is what we're really interested in, because a lot of times the y-intercept is outside of our range of data anyway. We have to extrapolate to get to that y-intercept, so we really aren't so interested in if the y-intercept is super accurate, but the slope of the regression line, that's what we want to hypothesize test about, and that's essentially what we're going to be doing. And again, a lot of these slides are just kind of trying to bridge that gap between hypothesis testing and linear regression. That, gosh, with everything else, we've always had a sample, and then we've tried to figure out what the population, like we got a sample mean, and we tried to figure out what the population mean was, and that's what we hypothesized about. We had a sample proportion, and we tried to estimate the true population proportion. Well, here we're going to have a sample slope based on our data, and we're going to try to hypothesize about the true slope of the best regression line for all the data. Okay, if we had the entire population of data, not just a sample of people where we compared waist size and percent of body fat. Basically, if we want to think about this, is we think that for every and using our example here, for every person who has, say, for example, a 38-inch waist, okay? So if we looked at all the 38-inch waists of our sample, we know that at 38 inches, there was a pretty good scatter of what's going on. And this histogram might represent the distribution of percent body fat for people with 38-inch waists. And what we could do is then at every waist measurement, we get a slightly different scatter plot or histogram of distributions. Now that's a weird looking graph, isn't it? Okay, but it's to give you an idea that it's not the same at every point. And again, with waist size here, we're just putting these scatter or histograms in at specific intervals. There's actually one at every point along the line. So there'd be another little histogram like right in the middle here, and another one there, and another one there. So they're all slightly different histograms depending on the distribution at that particular point. Now, the nice thing is that they tend to be overall approximately normal. Down here, this one actually is more inverted normal, but overall, they tend to be approximately normal. Now, the model is assuming the means of the distributions of percent body fat for each waist size fall along the line, even though the individuals are scattered around it. The model is not perfect, but it may be useful. Remember that line? No model is perfect, but some models are useful. That's what we're looking for. We've got all the values in the population. We could find the slope and intercept of the idealized regression line explicitly by using each least squares. But we don't have the entire population, we just have a sample. So what we want to do is we want to find our actual, or estimate our actual regression line, which instead of using our equation that we just wrote here, we're now going to write using Greek letters instead of regular Roman letters here. So instead of y hat, well, y bar we normally use there. We're going to use mu because that's going to be our mean of y. And instead of b, we use the Greek beta, which looks like a B. Looks like a fancy capital B with a tail, but it's a beta. And all that is saying, okay, that's the true population intercept, the true population slope of the best idealized regression line. Now, with all models, we have errors. So if we look at the errors to find the model, we're going to denote that error with the Greek letter eta, or I think that's eta, isn't it? My Greek is weak. I think that's the eta. Eta came to mind right away. But anyway, now I'm questioning myself. But anyway, that fancy little e, or backwards 3, I think of it as a backwards 3. So talk about the error. And now that is probably the true for each data point. Why? There's always going to be an error. And that error is our residual. Okay? So this point really just represents the amount of residual for any particular data point. Notice they're not at mu here anymore, we're at y. That's not going to be super important. All right? That's not super important. But we can hypothesize still about the slope of a regression line. In order to hypothesize about the slope of a regression line, guess what? We have to have assumptions and conditions, just like for everything else. In this case, we have to be very careful about the order in which we check the conditions, because if some of our initial assumptions are not true, it makes no sense to check our later ones. So this is one of the few times where the order in which we check the conditions, in fact, the only time I think in which the order we check them is true. The first is a straight enough condition. And we saw this before when we were doing a regression line. We always had that straight enough condition. Is my data roughly linear in its organization when we look at the scatter plot? If it's not linear, then stop. Okay, obviously, if we have a truly curved relationship in our scatter plot, we don't want to do this. It's not going to give me good data. So that linearity assumption, the straight enough condition, is really important. The next condition is quantitative data. Is this just like in chi-squared, we have to have counts of categorical data? For this, we have to have quantitative data on both axes, which is always required for a regression. So that straight enough condition and the quantitative data condition, obviously, those are things that we checked before when we did linear regression, so it's not a big deal. Random condition, they should be random representatives of the sample, nothing new there. The residuals technically are not a condition, but we should always check residuals when we do that. Make sure there's not a pattern to the residuals. That is a wonderfully amorphous pattern. That's like an idealized almost pattern to the residuals that we're seeing here. Does the plot thicken thing? We looked at that. Is the spread uniform, or do the residuals narrow on one end or the other? Like, do I have, like, we don't want to see a residual plot that's really widely scattered and then becomes very narrow down there, or vice versa. All right, that's still considered some sort of a pattern. So that's the old does the plot thicken thing from our chapter on that. The nearly normal condition, if you check a histogram of the residuals, which can be kind of tricky to find, and the outlier condition, check to see if there are any outliers. Now, every time I've seen this come up, and quite honestly, this whole idea of testing a regression line doesn't often come up. And the reality is, every time it has come up, generally they make a statement saying all conditions are met for inference. So then you don't have to check the conditions because you get that part of your A, you just say prompt states all conditions are met. Boom, done. Okay? So don't sweat these conditions so much because it's not going to be that big of a deal for us, I don't think. I've never seen it where it comes in where they say, did you check the normal distribution of the residuals? Well, no, nobody. It would take too long. I mean, that's why it's not going to be an issue, because it would take you way, way, way too long to do that, where you have about 10 minutes per question. There's just no way you could do that. So don't sweat the conditions too much. Again, the idealized regression line looks like this, where we have a perfectly bell-shaped curve at every point along the line. Of course, that's the idealized situation. It never actually happens. We get our little histograms instead that are some better at nearly normal than other. But it does lead us to a question. What comes first with regressions? It's a chicken or the egg type question. The best way to check the conditions is with the residuals. But we get the residuals only after we compute the regression. So we don't know if the regression's any good until we check the residuals, but we don't know what the residuals are until we calculate the regression. Oops. Total chicken and egg situation. So we work in the order. We make a scatter plot of the data to check straight enough condition. That always comes first. If the data are straight enough, we fit a regression line, find the residuals and the predicted values, and make a scatter plot of the residuals. And again, we can do that in Desmos. But again, you won't have to do that as part of your exam, I'm 99% sure. And if the data is measured over time, plot the residuals against time to check for evidence of patterns that might suggest they are not independent. So, see if there are seasonal differences or things like that. If the scatter plot looks okay, then make a histogram and normal probability plot of the residuals to check the nearly normal condition. Again, probably will never have to do that. If all the conditions seem to be satisfied, go ahead with the inference. So that is essentially the setup of what's going on here. And that's really all we have for day 1. Day 2, now we're going to actually start looking at how we actually run the whole hypothesis test. And quite honestly, we 99% of the time run this based on computer output. Okay, it'll give us the regression line, and then, if you recall, and I don't have my book, here's my book. So this is a time where you could go look at some stuff from our linear regression chapter. I'm probably getting ahead of myself to what we're going to talk about tomorrow. But turn to page 198 in your book. 198. Looks like that. And there's a computer print out there. And Nick never showed up today. Okay. And remember, we got this computer output that we had to learn how to read so we could do a regression model where it says the dependent variable is total fat. This was a total fat versus protein in a hamburgers or something like that. I don't remember exactly what this data was. Yeah, it was total fat versus protein. So dependent variable is total fat, so that's fat hat, which I always think is fun to say, fat hat. Equals, and then the intercept, that's my B naught, equals 6.83 plus 0.971 times protein, because that's my independent variable. Okay? What I want you to notice is the area that's circled down here on the right, where it says we'll deal with all of this later in the book. We are now later in the book. Okay? And what is it looking? It's giving you the standard error of the coefficient. Okay, it's our standard deviation, basically. So we've got our mean and our standard deviation, our t ratio, which is our t value, and our p-value, which is basically what is the probability of getting this or something more extreme, given that the true slope is 0.97. So we're seeing here the 0.97 is our mean. The 0.12 is our standard deviation. My t-score for this is 8.04 for that slope, which means there's a less than 0.001 p-value, so if we were hypothesized testing this at p equals 0.05, alpha equals 0.05, we would reject the null hypothesis and say that something's going on here. Okay? You also get a standard error and a t ratio and a p-value on the intercept, but again, we tend to ignore those because the intercept is usually not within our range of data. So that only becomes interesting if x equals 0 is in our data set. In many cases, it's not. Like if I look at that comparison of waist size and percent body fat, That's between like 30 and 48-inch wastes. That's not 0-inch waste doesn't really come into play because it's not reasonable. I mean, the y-intercept is meaningless there because nobody has a 0-inch waste. It's just not even physically possible. So that's kind of what's going on with that situation. But that's essentially where we're heading tomorrow is working on reading those things. And 99% of what we do when we look at these types of problems, flipping forward, is looking at that sort of thing and interpreting those results. We do not do any manual calculations of these things. One of the interesting things we'll get into is that the degrees of freedom for this test is actually n-2. We'll talk about that tomorrow. And so you probably want to read through the rest of this chapter. That's probably the most important thing that you should do at this point. But again, remember that as you're looking at all these calculations and values and stuff like that, 99% of the time, they will tell you all conditions for inference are met, and here's the computer output. Give me an interpretation of what's going on. So where you may see this come up is if we get to the linear regression question on the free response section, because there's always a regression question. They may walk you through the process. They'll give you the computer output. And they'll ask you to do all sorts of interpretation. What is the interpretation of the slope? What is the interpretation of this? What is the interpretation of that? And you get all these questions that have nothing to do with inference. And then for the final part of that question, they'll say, all conditions of inference have been met. Interpret the p-value on the slope. Okay? So you'll get a question like that. And that's what we'll spend more time tomorrow talking about, how we do that. So good stuff to know, but in practice on the exam, for what we really need to know is the big thing is we need to know what that computer output means and have a good solid understanding of what a linear regression is actually doing, that it's just trying to give you a predictive model based on a scatter plot. The best predictive model. So, how do we feel diving back into that world of linear regression? Do we feel like, oh yeah, I kind of remember this stuff?